Hello students, today we will discuss some topic about the angle modulation, introduction to the angle modulation, that is frequency modulation and phase modulation. Already in my videos, in my lectures, I have discussed many things about the amplitude modulation, and today we will go for the angle modulation. So in this video we will study the expressions of angle modulations like phase modulation and frequency modulation, their relations, how we can generate PM from FM, how we can generate FM from PM, and also we will listen the narrowband and wideband generation of FM and PM, their expressions. So let's start, and hope we will enjoy the video of the ECE. So let's go, like, subscribe and share. So let's start. So angle modulation. What is angle modulation? We have already studied about the AM, that is amplitude modulation, and the angle modulation means frequency and phase modulation, FM and PM. What is angle modulation? It can be defined as the process in which the total phase angle of a carrier wave is varied in accordance with the instantaneous value of the message signal. But in that case, the amplitude of the carrier signal in both FM and PM should be constant. So going for the expressions, let us consider the carrier signal that is given as your CT equals to A cos omega CT plus theta 0. What is theta 0? Theta 0 is my phase angle, omega c is the carrier frequency, and the maximum amplitude of the carrier is A. Now if we substitute omega ct plus theta 0 equals to phi, then we can get A cos phi, where phi is the total phase angle. So if I want to have the angle modulation, so we need to modulate that phi keeping A constant. So in this total phase angle phi having two different parts, what are these parts? These two parts are omega ct, that is frequency part, and another is theta 0, that is my phase part. So angle modulation, if I modulate this omega ct part, it will become frequency modulation. If I modulate this theta 0 part, it will become phase modulation. So we can say that the angle modulation can be defined in two types, that is phase modulation and frequency modulation. Now I am coming to the phase modulation. What is phase modulation? It's a type of angle modulation where the phase angle, that is phi, or the phase part theta 0 is modulated, where we keep the amplitude and the frequency of the unmodulated carrier signal constant. So here you can see ct equals to A cos omega ct plus theta 0, which is A cos phi. Now neglecting theta 0, we can get the total phase angle of the unmodulated carrier is phi equals to omega ct. Now according to the phase modulation, the angle phi is varied linearly with the message signal xt. So this is my instantaneous value of the phase angle, which I can write phi I equals to omega ct plus kp xt, where omega c is the carrier frequency and kp is the proportionality constant, which is known as my phase sensitivity, and xt is obviously your message signal. However, the expression of the unmodulated carrier wave is my ct equals to A cos phi. So the expression for phase modulated wave will be A cos phi I, which is the instantaneous value of the phase angle. So the modulated PM signal can be written as this: st equals to A cos omega ct plus kp xt, where kp is the phase sensitivity, right? So now just the introduction of the frequency modulation, where I am varying the frequency of the unmodulated carrier wave, where we need to keep the phase and the amplitude constant of that carrier. So now in that case we need to confirm the instantaneous frequency omega I equals to omega c plus kf xt, where kf is the frequency sensitivity and it is multiplied with the message signal. So according to the value of the message signal, my instantaneous frequency will be changed. So again we know that Ct equals to a cos phi. So the expression for frequency modulated wave will be a cos phi I, where phi is omega ct plus theta 0. So d phi dt is what? Omega c, as theta 0 is constant in case of frequency modulation. We have already said the phase and the amplitude will be constant. So phi equals to integration of the omega c dt. So what is phi I? Phi I will be integration of omega I dt. So just putting the value of omega I here, we can easily derive that phi I equals to omega ct plus kf integration of xt dt. So this is the expression of Fm, a cos omega ct plus kf integration xt dt. So almost similar to Pm, but in case of Fm there is an integration of the message signal. In case of Pm there is no integration. So there should be some relationship between Fm and Pm. Just this portion is a little bit of changed here. So we can now go for the relationship between Pm and Fm, where we will see how Fm is generated using Pm and how Pm is generated using Fm. Here we can see the angle modulated wave st equals to a cos phi I. Phi I is the instantaneous value of the total phase angle. Now for Pm we have already seen the expressions, and for Fm we also have seen the expressions. Now if we want to generate Fm using Pm, now this is my expression of Fm, this is Pm. So Fm using Pm, so already I will use this one is my Pm. So if I integrate this portion and passes through a phase modulator, so it will become this. So Fm will be generated using Pm. So here we go. So first integrating the xt, we are having integration of xt dt, and this is passed through a phase modulator to generate the Fm. And the same principle is applicable when we will generate Pm using Fm. Just in place of integrator there will be a differentiator. So after differentiating it will become dxt dt, like that. And if we pass it through a frequency modulator, what is the expression? It will be, if the input is xt, it will be integrated. So if the input is dxt dt, it will also again be integrated and it will become xt. So if it becomes xt, it will become Pm. So this is my Pm using Fm. So that is the relationship of Fm and Pm. Here we have seen we can generate Fm using Pm and we can generate Pm using Fm. So let's have a discuss between the singleton Fm, how we can generate it, what is its expression, and from this expressions and this derivation we can also learn about the modulation index of the Fm, which we have already studied in the amplitude modulation technique. So here we go for the singleton modulation of frequency, that is singleton Fm. So let's consider the carrier signal. Unmodulated carrier signal is a cos omega ct, right? So the modulating signal or message signal B, xt equals to Vm cos omega mt, where Vm is the maximum amplitude of the message signal and omega m is the frequency of message signal. Only a single frequency is present here, that is why it is known as singleton Fm. So we have already studied that the expression for Fm is st equals to a cos phi I, where phi I is the instantaneous phase angle of the modulated wave. So instantaneous frequency is given by omega I equals to omega c kf xt. So putting the value of xt here, we can get omega I equals to omega c plus kf vm cos omega mt. Now the term frequency deviation, another important term in case of FM, it is defined as omega del omega, that is frequency deviation. How much the frequency will be changed is my mod of kf xt max. What is the maximum value of xt? Kf is a constant. Maximum value of xt is Vm, so it is become del omega equals to kf into Vm. So my instantaneous frequency omega equals to omega c plus del omega cos omega mt. So what is instantaneous phase angle? It is the integration of omega I dt. So it is easily becomes omega cd plus del omega by omega m sin omega mt, like that. Now what is this del omega by omega m? This is my modulation index in case of FM, which is defined as the ratio of frequency deviation to modulating frequency. Frequency deviation is del omega, modulating frequency is omega m. So del omega by omega m is my modulation index, which is denoted by this one m suffix f, that is mf. So del I is equals to omega ct plus mf sin omega mt. So my general expression for single tone frequency modulation becomes a cos omega ct plus mf sin omega mt. This is my overall single tone frequency modulation expression. Now if we see a numerical problem here, you can see the single tone FM is represented by the equation if Vt equals to 12 cos 6 into 10 to the power 80 plus 5 sin 1250 t. You have to determine the carrier frequency, message signal frequency, modulation index, maximum deviation and the power dissipate in 10 ohm resistor. So what is carrier frequency? It is obviously this one. This is omega ct. Omega c equals to 6 into 10 to the power 8. So fc will just omega c by 2 pi and it's become 95 megahertz. Message signal again from here omega mt, omega m equals to 1250, so fm equals to 1250 by 2 pi, so it's become 199 hertz. What is mf? From the expression you can see the mf is obviously here 5, so the modulation index is my 5. Then my frequency deviation, that is maximum deviation is the frequency deviation. So what is mf? Mf is del omega by omega m, which can be written as del f by fm. We know the value of fm, which we have already calculated. We have no value the mf, so we can easily calculate the value of del f, which is my 495 hertz. And finally the power dissipation in a 10 ohm resistor. This is my fifth part, and it's become Vrms square by capital R. What is Vrms? My maximum value of the voltage was 12, so the RMS value of the voltage would be 12 by root 2. So 12 by root 2 whole square by 10 ohm resistor, that is 10, and it would become 7.2 watt. So that's how we can easily calculate the numerical problem of the single tone frequency modulation. Now let us have a discussion with the types of FM and PM. In that part we will see how the narrowband FM PM and the wideband FM PM is generated. In case of narrowband, the KF by or the KP, whatever the sensitivity of the frequency or phase, it will be very very small, and hence the bandwidth also become very very narrow. For the wideband, obviously the value of KF or KP, the sensitivity of phase or frequency, is very large. So in that case the bandwidth also will be very large for both FM and PM. Now go for the narrowband FM or PM. Now we know the general expression for FM wave in phasor form, that is CFM equals to A e to the power j omega ct plus kf yt, where yt is my message signal. However, for the narrowband the kf(yt) will be very less than 1, because kf is having a very small value. So e to the power j kf(yt) will become 1 plus j kf(yt) from the theory. So the expression for fm would become like this. From here, e to the power j omega ct plus kf(yt) we can derive like this: e to the power j omega ct into e to the power j kf(yt). The e to the power j kf(yt) will become 1 plus j kf(yt). So the real part of fm would be like this: the real part of c fm, which is a cos omega ct minus a kf(yt) sin omega ct. So in the similar fashion, we can have the expression of narrowband fm, which narrowband pm, which is a cos omega ct minus a kpxt sin omega ct. So these are the expressions of narrowband fm and pm signal, which are quite similar to each other with a little modification. So this is my block diagram of the narrowband fm generation. Here you can see in this video, in this picture, there is a carrier signal generator which is generating a signal a cos omega ct, and it is going through to the output of summation, as my fm narrowband expression is a cos omega ct minus a kf(yt) sin omega ct. So a cos omega ct is already here, have reached. And now if we make a 90-degree phase shift, it would become minus a sin omega ct, because 90-degree phase shift means a cos omega ct plus 90 degrees, so cos theta plus 90 means minus sin theta, so it would become minus a sin omega ct. Now if we integrate this xt, my yt is the integration of xt, so after going through to the balanced modulator, it would be multiplied, so that would become minus a kf(yt) sin omega ct, where kf is the frequency sensitivity and it is generated by this balanced modulator. And after passing through this, after the summation with a cos omega ct, it would become like this, and this is my generation of narrow band fm. And in the similar way, we can generate the narrowband pm, where the expression is a cos omega ct minus a kpxt. Same fashion, only no integration part, no yt, direct xt would be there. So my pm signal would become a cos omega ct minus a kpxt sin omega ct. So if we derive this expression of the singleton narrowband fm, we have already generated this STFM, where yt is the integration of the message signal xt dt, where xt is any message signal. Now for singleton narrowband FM, we would take a single frequency where xt equals to Vm cos omega mt, so yt would become integration of that, so yt would become Vm by omega m sin omega mt. So just replace the value of yt in that expression and we would get a expression like this. So STFM become a cos omega ct minus a kf Vm by omega m sin omega t sin omega ct. And already we have discussed about the modulation index of that fm, which is kf Vm by omega m. Kf Vm was the del omega, so del omega by omega m is my modulation index, and it would become like this. So a cos omega ct minus a mf sin omega mt into sin omega ct. So that's how we can generate the narrow band fm. And in the similar way, we can generate a single tone narrowband PM signal. So today's video was about the introduction of FM and PM. In the next video, we would discuss the topic of how to generate and how to detect this FM and PM signal. This was my only the introduction of the FM and PM, their expressions, the modulation index, and how to generate the narrow band FM and PM, and also the relationship of the FM and PM. So thank you. Thank you for listening. Obviously, if you like my video, then share it, make subscribe, and spread these videos of my easy ECE, and I think you would stay very easy, not a complex part, so your ECE is very easy. Thank you.